Right, welcome again to Building Stuff. Today we're going to look at what was technically my first Tesla coil. It was built with a neon sign transformer, 12,000 volt neon sign transformer, and all the components at the time when I got it initially working was connected using test leads and impermanently connected. So here's a video of the Tesla coil in operation with that 12 volt neon sign transformer. Now, what subsequently happened was that during tuning and tweaking and trying to get better discharges from the coil, the neon sign transformer died, and subsequently it was put aside, and I worked on the other microwave oven transformer Tesla coils that you've seen in the other videos. And then I returned to this and made it more robust, actually with 4 microwave transformers. So that's going to give me about 8,400 volts. And then I added a big capacitor bank. Now, originally it was running only on a single 50,000 volt rated 2.2 nanofarad capacitor, and it was producing discharges. But what happened? Well, what I've done is I've added this big capacitor bank. It's a ceramic capacitor bank. This adds up to about, I think, 30 nanofarads. 30 nanofarads. Actually, it reads only about nearly 23 nanofarads. And everything was neatly tied down, screwed down, everything in its place, spark gaps and everything done. And yet, since the operation with the neon sign transformer, I haven't been able to get it working again. Now, I'm just wondering why, and going through the possibilities as to why it won't operate. And I think I have the solution at the moment. As you can see, this is a pretty small secondary coil. Only measures about 32 centimeters in the coil length, and a very small top load, and a spherical one at that. And so the LC quality, or the LC component of the resonant frequency of that, is going to be pretty high, but the LC component is quite low. Now, going back to our resonating frequency formula, the frequency is 1 over 2 pi times the square root of LC. Now, the smaller the LC, the bigger the higher the frequency will be. But the LC is quite low in this particular Tesla coil, so consequently, to resonate, the primary and the primary capacitor is going to have to be pretty low. So that's why it was running only on 2.2 nanofarad capacitor and was working. And so I suspect this 20-something, 23 nanofarad capacitor is way too high for the system. I think if I change that for a very small value, about 2.23 nanofarad, I should be able to get it working again. Let's see how we go. Okay, off camera for about an hour and a half, I spent time tweaking, adjusting, tuning. I looked through an old photo. I didn't quite have a good video besides that one that I showed you of the operation, but I had a photo of the unit set up, and it was more than 2.2. It was 2 of those blue capacitors, so I've rigged up an equivalent there, so about 4 nanofarads. Adjusting the spark gap. This sort of spark gap seems to be extremely sensitive, small adjustments affecting the operation. And of course, a lot of tests on the tuning, tapping different turns on the primary. And even then, I had trouble getting it to work. We had high voltage arcing across the spark gap, but nothing was happening. And then I thought about how much current this set of 4 microwave transformers was delivering. So these can deliver up to about 400 or 500 milliamps, which is significantly more than the 30 milliamp neon sign transformer, which means that, well, I was thinking about it, it was delivering way too much current and charging the capacitors up probably too quickly, and not giving time for the capacitor to discharge through the LC, the inductor circuit, and it was probably always charged instead of oscillating. So what I had to do was, so those were the 2 toroidal inductors that I was using for current limiting. but they seem to not be limiting the current enough in this instance for this small Tesla coil with the small capacitors. And so I'm using a faulty microwave transformer primary to do that. And I found that with this, I've got some sort of operation, at least some sort of discharge from the breakout point. Now, it's not impressive. Let's have a quick look at that. Not impressive at all. About 5 centimeters of discharge. That seems to be the best output that I've been able to attain with it at this present time. Now, that's actually even less impressive than some of those Resonant solid state Tesla coils that you can get online, small ones for about $20, those music Tesla coils. And considering how much time and money we've spent on this, that's extremely disappointing. Just trying to get back to those discharges that I was getting from the neon sign transformer. Now, thinking about it also, the neon sign transformer is 12,000 volts. This is 8,400 or so. So we expect the discharges may be a little bit shorter because it's only 2/3 the input high voltage. But even so, this is very underwhelming. Now, 1 or 2 more things under my belt to try. I looked through the photo. The previous spark gap I used when I had this operating better was this one with the bigger surface area on the spark gap. I might swap that and see if that performs any better. I have tried increasing the capacitance a little bit with more capacitors, but no significant improvement on the output despite tuning and everything. Now, I've tried the old spark gap with the wider contacts and blowing air over it. No significant improvements on the other spark gap that I had there. I was thinking about what the current limiting inductor was doing to the input voltage, and let's have a look at that. The current limiting inductor is limiting the input current to about 76 volt AC. The actual main line voltage is 244 volts. So you see what's happening is that the current limiting inductor is reducing the voltage that appears across the 4 microwave transformers down to about 74 volts, which means the output of those transformers is not going to be 2,100 volts each. It's going to be a little less than 1/3 of that. So getting probably about only 700 volts. This is probably why I'm not getting the discharges that I should be seeing. The solution will be in reducing the current, but yet maintaining the voltage input to the transformers. So each of those microwave transformers producing probably about 700 volts, total of 4, about 2,800 volts, being stepped up by this very small secondary. That's probably why the discharges are so short. So what do I need? I need a neon sign transformer, which will present 12,000 volts across the primary to be stepped up. So that's going to give me about 3 times as much, or 4 times as much voltage at the primary, and probably bigger discharges at the breakout point. And the neon sign transformer will also have the limited current output, about 30 milliamps, that won't overwhelm the very small capacitor. Best performance from this Tesla coil. So the simple solution for this Tesla coil, if I wanted to create big discharges, is to wind a new, bigger secondary and put a bigger top load on it. But for this coil, I wasn't necessarily aiming for that, because I've got all those other Tesla coils that can do that. This one is sentimental to a degree. I bought the neon sign transformer some 30 years ago at a flea market, along with this fiberglass tubing, which was sold to me at a electronics flea market, with the seller telling me that I could create a Tesla coil from that, and I wanted to keep that sentiment in recreating this Tesla coil, just trying to get back to those longer spark that I had when I had the neon sign transformer. Okay, so that was my very first attempt at a Tesla coil, and as you saw, may have seen in the previous several videos where I presented all the other Tesla coils, you may want to refer to those. In the next video, I'm going to share with you a comparison of two different sized secondary coils and discuss whether that makes a difference, the size of them makes a difference at all. Anyway, please tune in, please like and subscribe and follow us on this Tesla coil journey. See you next time.